Bond line formulas. This will be a method that will allow us to draw organic molecules without having to unknowingly spell out every single hydrogen and every single carbon that's present in the molecule. The process is actually rather simple. All you do is not write that carbon and those hydrogens bound to the carbon. So in the case of CH3, all you have to draw is that simple line that represents the bond between the carbon and carbon elements of the structure. And notice that I'm not writing the carbon, I'm not writing the hydrogens. And over here, the same thing. This will be line going up, line going down, going up, going down, going up, going down, and you end up with this structure right here. Each one of the ends, as well as the corners that you have in the structures, represent a carbon atom. So in the structure you have 1, 2, 3, 4, 5, 6, 7 carbons. You have 1, 2, 3, 4, 5, 6, 7 carbons. And the same thing here. You literally take that structure and remove each one of the carbon and hydrogens bound to those carbons, and you end up with your bond line formula. And this is a lot easier to draw, a much faster thing to draw than having to actually spell out each one of the symbols for the elements. Now, one thing to be said though is that this format only applies to carbon and hydrogen bound to carbon. If you have an element other than carbon as a central element, you have to actually write it out. And if you have hydrogen bound to anything else other than carbon, you have to write out that hydrogen as well. Okay, now in respect to the connections, one thing that I want you to get familiar with, because from here on out we're going to be drawing the molecules in the bond line formula shape. What I want you to remember is that carbon has to have 4 bonds. Every time it's going to have 4 bonds, especially if you have a neutral structure. So what that means is that when you look at these bond line structures and you concentrate on any one corner or any one end, all you have to ask yourself is how many connections does that carbon currently have? And in the case of the middle carbons here, this carbon has 1 and 2 connections. So subtracting those 2 connections from 4, which is the ideal number of bonds, tells you how many hydrogens this carbon has to have. All right, so we're gonna try this out with an example. Okay, so we have the formula right here. The bond formula will basically be the same thing, except that you don't draw the carbons, you don't draw the hydrogens. Any other atom that appears, you have to draw. And if hydrogen is bound to anything else other than carbon, you draw the hydrogen. So that means that we go from this structure to the one right here. And notice once again that the oxygen up here, the chlorine down there, oxygen here, and nitrogen there are still represented as such in the bond line structure. In addition to it, the hydrogen, which is next to the oxygen, is understood to be bound to that oxygen. Same thing for the nitrogen here. Hydrogen next to the nitrogen is understood to be bound to the nitrogen. So those 2 hydrogens are still drawn out. But every other carbon and hydrogen's bond to carbon are omitted. The overall structure and shape is still represented in the structure, but we are just keeping the relevant bond line segment. All right, now what we're going to do is we're going to take a molecule like the one right here, and we're going to try to determine, which carbons have what number of hydrogens. And the idea is that if you do have 3 directions on that carbon, you only need an extra hydrogen to complete the octet. And in the particular structure shown here, all the ones highlighted in red are carbons that have already 3 directions. It could be 2 other carbon atoms, it could be 2 oxygen atoms, or anything else other than hydrogen. In that regard, those carbons are understood to have that hydrogen present in there to complete the octet. We don't draw them in the bond line structure, but it is understood that this carbon has 1 H, that carbon has 1 H, 1 H, 1 H, 1 H, and 1 H, right? Now, for carbons that only have 2 directions coming out of them, we have to have 2 hydrogens on them. And specifically, we're talking about these carbons that have that bent structure, right? So out of this carbon, we have 2 directions coming out of them, or 2 bonds coming out of it. So we need to have 2 hydrogens to complete the octet. So we'll have 2 hydrogens over here. We will also have 2 hydrogens down there, and down there, because those carbons only have 2 directions coming out of them in the bond line structure. If the carbon in question is terminal, meaning that it only has one direction, like the band, you will have to add 3 hydrogens, or it will have to be understood that 3 hydrogens are present on that carbon. So this terminal carbon, only one direction coming out of it, 3 hydrogens. Terminal carbon, 3 hydrogens. Terminal carbon, terminal carbon, terminal carbon, terminal carbon, and terminal carbon, 3 hydrogens. And last but not least, if the carbon in question already has 4 directions, then it's understood that there is no hydrogens on that carbon. In particular, we're talking about the carbon right here. This carbon already has 4 directions coming out of it to non-hydrogen atoms. It already has a fulfilled octet. You do not need to have any more hydrogens on that carbon. So that's the thing to be, aware of. So let's do one more example of that sort to make sure that the concept is, concrete. All right, so first look at the structure. We'll take a look at those quaternary carbons, the ones that have 4 bonds already. And in the structure, all of the following carbons highlighted in pink here represent carbons that already have 4 bonds or a full octet, so they do not need hydrogens. And notice right here that even though the directions for some of these carbons are not 4, so this carbon technically only has 3 directions, but it still has 4 bonds altogether and 8 electrons altogether. So it does have a full octet. It doesn't need an extra hydrogen to fulfill the octet. So all of these are what we call quaternary carbons. Same thing here for this carbon. 2 directions, but you have a triple bond and then you have a single bond, altogether 8 electrons on that carbon. Okay, now for carbons that have 3 bonds altogether, we need to have 1 hydrogen on them. And the following carbons represent that situation. Specifically, the carbons here on the left side, you have a carbon with 1, 2, 3 bonds, carbon with 1, 2, 3 bonds. So both of those carbons have to have 1 hydrogen to fulfill their octet. And down here, the carbon at the very end of that triple bond, it only has the triple bond, which is only 6 electrons, so it must have a hydrogen to complete its octet. All right, now 2 bonds equate to 2 hydrogens. We look for those bent lines, right? So here is a bent line that's got 2 bonds around the carbon. That's got to have a CH2. Bent line, CH2. Bent line, CH2. Bent line, CH2, 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 right? So all of those elements contain that CH2 associated with the structure. And as you can see, especially in compact structures like this one, writing out the carbon and hydrogens can become rather ugly. I mean, look at this thing. Those 2 hydrogens from this carbon are kind of like overlapping with the carbon up here. So things start looking ugly. And this is another reason why the bond line formulas are so popular in organic chemistry. You get rid of all the clutter and you make things much more concise, pristine, and looking better. All right, so the last one. If we have 1 bond, meaning that the carbon is terminal, we associate it with 3 hydrogens being present on that carbon. So terminal carbon right here, terminal carbon there. Now this carbon, of course, is terminal, but it is part of a triple bond, so that will not have to have 3 hydrogens. If you put 3 hydrogens on this carbon, you gave me 12 electrons on a carbon, which needless to say is way more than 8, and you have not only violated the octet rule, you have decimated it. Right? So don't do that. Be careful. Make sure that you only have 4 bonds altogether. All right, so in the structure, the only terminal carbons are the ones highlighted here in green. So those are the ones that have 3 hydrogens. Okay, so that's the idea with the bond line formula. Get used to that. We're going to be utilizing the bond line formulas throughout the rest of the semester. And for that matter, in the next section, the second part of organic chemistry. Okay, so we got one more topic to cover before the end of this lecture, so I'll see you in the next video.